This video is an introduction to rational functions. And we'll start with the definition of a rational function. A rational function is the division of two polynomial functions. Another way we could explain it would be a fraction with a polynomial numerator and denominator. The domain of a rational function consists of all real numbers except those for which the denominator is 0. We recently worked with polynomial functions, and I wanted to review the definition of continuous because all polynomial functions are continuous, which means all of the domain values are defined and will produce range values. Rational functions, however, are not necessarily continuous. Here's an example of a rational function, and I can demonstrate that by trying to trace this. There will be a point where I have to pick up my marker to continue tracing from left to right. So somewhere in here there's a domain value that's undefined that does not produce a range value, which creates what we call a discontinuity. Now while we have these two graphs up here, let's make a connection between one of the similarities between polynomial and rational functions. The numerator of the rational function will lead us to the roots, just as all the factors of a polynomial function led us to the root. The factors of our numerator will also. So let's look at a single root at -1, a triple root at +1, and a double root at +4. In this rational function we have a single root at -2 and a single root at +1. In just a bit we'll start examining the effects that the factors of the denominator have on the graph. Roots of a rational function can be found by solving when we put the numerator set equal to 0, but there are exceptions. Because rational functions are not necessarily continuous, we do have different names for different discontinuities. The first we're going to look at is called a removable discontinuity. Some textbooks refer to it as a point discontinuity. I will often refer to it as a hole in the graph. Now if we look at our numerator and denominator, each one is a polynomial. A technique we will always want to try to use when we're examining polynomials is factoring. If possible, we always want to factor numerator and denominator. And now what happens in this case is that we end up with a common factor in the numerator and denominator. That is what leads us to these removable discontinuities or holes in the graph. So we take that factor, we set it equal to 0. This tells us that we will have a discontinuity at x equals 0. Now what we have left over after we reduce is the graph of a linear function. So there actually is no point on the graph at x equals 0. The rest of the graph is the line 2x plus 1. So again, to summarize holes, or point discontinuities, holes occur in the graph of a rational function when the numerator and denominator have common factors. The holes occur at the x values that make the common factors equal to 0. Another type of discontinuity that we will find in rational functions are called infinite discontinuities. These are vertical asymptotes. Vertical asymptotes occur when the following condition is met. The denominator of the simplified rational function is equal to 0. So when we're searching for vertical asymptotes, we want to make sure that we had first gone through the process of locating the holes in the graph. So we are without those singular discontinuities, but we do have two factors, x plus 6 and x minus 2 in the denominator, which we will set equal to 0 and solve. So this is the equation of a vertical line, and this is the equation of a vertical line. These are vertical asymptotes, also called infinite discontinuities. Now, not every asymptote is a result of undefined domain values. There are other kinds of asymptotes, horizontal. So in this case, the graph would approach but not reach this horizontal line. Vertical asymptotes we mentioned on the previous slide. And a third type of asymptote is called a slant asymptote. Some textbooks will refer to this as an oblique asymptote. One difference between horizontal and slant asymptotes when compared with vertical asymptotes is the graph of a rational function can intersect a horizontal or slant asymptote, but the graph of a rational function will never intersect a vertical asymptote. The technique for finding the location of intersections, if they do exist, between the graph of a rational function and a horizontal or slant asymptote is just some simple algebra. You would set the rational function equal to the equation of either the horizontal asymptote or the slant asymptote and then solve for x. Now for finding horizontal or slant asymptotes, it's a little bit more complicated than finding verticals. Here is a summary of the techniques we'll use. So given a rational function where we have a polynomial numerator and a polynomial denominator, we will be examining n and m. These are the degrees of the numerator and denominator. The degree of the numerator is less than the degree of denominator, then the x-axis, the line y equals 0, is a horizontal asymptote. And when we find a horizontal or slant, we know that that is the only horizontal or slant of the graph. There will not be more than one. If the degrees are equal between numerator and denominator, then we take the leading coefficients, a over b, and that gives us a horizontal line. Now if n is greater than m, there will be no horizontal, but there might be a slope asymptote. So if our degree in the numerator is exactly one more than the degree in the denominator, that's when we know we'll have a slant asymptote, and we will find the equation of that slant asymptote by either using long division, numerator divided by denominator, or by using synthetic division. Let's look at an example. We'll use these guidelines to help us determine what kind of asymptotes we have. Now remember, we're only looking for horizontal or slant asymptotes. My degree of the numerator is 2, degree of the denominator is 3. That tells me that we have case 1 here, and our horizontal asymptote will be at y equals 0. That's the x-axis. In this example, we have the same degree, numerator and denominator. So that's case 2 here. If n equals m, then our horizontal asymptote will be 2 over 3. So there will be a horizontal line going through the y value 2/3, and that will be our horizontal asymptote. In this case, our numerator degree is greater than the denominator degree. So that tells us there is no horizontal. To check for a slant asymptote, we determine what's the difference between the degrees. If it's exactly 1, then we will have a slant asymptote. The only thing we're interested in is our quotient. We get y equals x plus 6. This is the equation of our slant asymptote. All right, let's go through a few examples to put some of these techniques all together. So we're given a rational function here, degree 3 divided by degree 2. First step is always to factor if possible. And now that I see we have a common factor. Remember, the common factor leads us to the removable discontinuity, or the hole in the graph at x equals 2. We then would reduce. I would see that at x equals -2, we have a vertical asymptote. Then to find roots, I would set my simplified numerator equal to 0. The line of y equals x, 1x plus 0, or y equals x, is my slant asymptote. So we have a hole where x is 2, there's a vertical asymptote at x equals -2, and our slant asymptote is y equals x. When we put it together, this is what our graph will look like. I think I made a mistake earlier. Y-intercept is at 2. 8 divided by 4 is 2, not 4. Test points will still be a valuable part. It turns out when we tried to solve this quadratic, we end up with imaginary roots, and what that tells us is the graph does not actually cross the x-axis. Now, to answer the question about whether or not the graph crosses the slant asymptote, what we would do is simply take the equation of the slant asymptote, and we would take our simplified rational function. We would then solve for x. And now you can see that when I subtract x squared from both sides and 2x from both sides, I get 4 equals 0, which tells me there are no solutions. So in this case, the asymptote would not be intersected by the graph. And here's our last example. Our rational function has polynomial numerator and denominator, both of the same degree. First, we want to try to factor, and it turns out both numerator and denominator factor. The common factor, x plus 5, leads us to a hole at x equals -5. Now we work with our simplified rational function. I can see that at x equals -2, there is a vertical asymptote and infinite discontinuity. At x equals 3, we have a root. My y-intercept, -3/2. If the degree of numerator and denominator are the same, that tells me that my horizontal asymptote does exist. So that's 1. There's our vertical asymptote, our horizontal asymptote. Here's our function, and don't forget, where was our hole located? At -5. There is a removable discontinuity right at x equals -5. And here again is a summary of important information for the graph of this rational function. Thanks for watching. Keep practicing.